I'm Pat Frank, and I'd like to thank Jane Orient for inviting me to speak with you today, and Willie Soon for recommending me to Jane. A couple of days ago, I asked Jeremy if there was a dress code for speakers, and he said no. He said most people wear ties, but if you want to wear a t-shirt, you can do that. So I'm wearing my chemistry t-shirt today, but I brought a tie along just to show you that I have one. So climate models really are the beating heart of the modern frenzy about carbon dioxide. And they're going to be the subject of the talk that I give today, the accuracy that they bring to bear on the subject. Here's an outline of the talk. We'll talk about the standard message and the enhanced greenhouse effect, the official representations of uncertainty and air temperature projections. We'll talk about extracting the greenhouse and then modeling the models, and talk about model cloud error and the neglected climate communication of reliability. And we'll end up with what is actually being predicted and how should we respond. This is the IPCC message. Human interference with the climate system is occurring, and climate change poses a risk for humans and natural systems. And really, this is the true message. If you don't repent, you're all going to die. And there's the fifth assessment report there, which is the Bible of the IPCC. Everybody knows what the IPCC is. So there's the encouraged response, right? Panic, please save me. But the proper response is, how do you know? And you can recognize Sherlock Holmes there, Basil Rathbone playing Sherlock Holmes. And that's the question we're going to ask, is how do they know that they're telling us is accurate? So the exemplified message is that it's extremely likely that human influence has been the dominant cause of the observed warming, and that the human influence has been detected in the warming of the atmosphere and the oceans and all the rest of it. And the NRDC, the National Resources Defense Council, is a very typical message of the green NGOs, which is carbon dioxide and other air pollution is collecting in the atmosphere, and it's working like a blanket, and unless we do something, the temperatures are going to go from 3 to 9 degrees. That's really an outlier, but they like to use that. And that global disaster is going to follow. So here is a slide that sort of summarizes the greenhouse effect. And you have solar energy comes in, most of it gets reflected away by the upper atmosphere and clouds. And about 235 watts per square meter makes it down to the surface where it warms the surface. And then the warm surface re-radiates infrared back up and it warms everything. So that, this 235 watts would give a black body radiation temperature of 255 Kelvin, but the true temperature down here is 14 degrees warmer than that, and the total greenhouse warming, the standard number is 33 degrees centigrade, warmer down here than the radiation temperature is at the top of the atmosphere. So how it works, increased greenhouse gases, mostly CO2, leads to increased temperature, which causes water to evaporate, puts more water vapor into the air, which causes further warming and leads to this effect. So here is a slide showing projections of future global warming given two different scenarios from the 2013 fifth IPCC report, Representative Concentration Pathways. There are four major ones, the 2.6, 4.5, 6.0, and 8.5, and these are the amount of CO2 that they project to be in the atmosphere by the year 2100. Here's the change in temperature for the 8.5 scenario and the 2.6 scenario, and here are the temperatures that are projected to occur as a consequence. The 8.5 is the favorite one to use, 4.1 degrees plus or minus 0.7. So I'll ask you to remember these plus or minuses here, about plus or minus half a degree uncertainty given by these shaded regions. So the legend for this figure is projections are shown for each RCP, representative concentration pathway, for the multi-model mean solid lines, the solid lines there, plus or minus 1.4 standard deviations, 5 to 95% certainties across the distribution of individual models based on annual means. So these shaded regions are the spread of model projections, and the dark lines are the averages. So what does that legend, plus or minus 1.4 standard deviations across the distribution of individual models based on annual means, what does that actually mean? Well, it means that they're showing the model average plus or minus the model standard deviation. It means that the typical general circulation model will project future temperatures within those shaded regions about 90% of the time, 1.64 standard deviations. It means the shaded regions are only telling us about the models, their projection divergence. That's a measure of precision. It means the shaded regions are not telling us about the model correctness, the accuracy of those projections, which is a measure of reliability. So when you see pictures such as this, this is from the AR fifth assessment report again of the global change during the 20th century in various regions of the world, with their pink and their blue shadings of natural forcings and forcings plus anthropogenic forcings, which show the 5 to 95% range of the stimulated response. Or like this is the RCPs showing how the temperatures will change all the way to the 24th century, depending upon the amount of CO2 that's emitted, all these different models that went into those simulations. And the shadings are the multi-model means, plus or minus 1.4 standard deviations. When you see plots like that, or like these with their model shadings, these are all divergence of the models around their means. You should realize that those spreads all just represent the precisions of the models and not the accuracy. It's not the reliability of those projections. But isn't reliability exactly what we need to know when evaluating projections of future climate change? However, no published study shows the uncertainties or errors propagated through a projection, a temperature projection made using a general circulation model. None of them. So the reliability of these projections is apparently unknown. So the rest of this talk is going to explore the physical reliability of GCM global average temperature projections. So what are the climate models actually projecting? This is a model of a climate model projection. And I'll show you what that is. This didn't spring directly from my head like Aphrodite's from the forehead of Zeus. There's a derivation for it, but I'm not going to go through that. I can show you a couple of slides about it at the end if anybody wants to know. So the change in temperature is equal to the fraction of warming due to carbon dioxide, 0.42, times the unperturbed greenhouse temperature at the surface, 33 Kelvin, you've already seen that, times the fractional change in greenhouse gas forcings. The forcings that I use all the time are for carbon dioxide, nitrous oxide, and methane, same as the IPCC does. So what this says is that GCM air temperature projections, what we're going to show, are a linear extrapolation of greenhouse gas forcing. That's all they are. So what does linear extrapolation of forcing actually mean? It's our climate model. It means that the equation of a straight line will duplicate climate model air temperature projections. Y equals mx. And if you put in a little bit of variation on x, you can put a little bit of variation in on the line. Coming up, climate model temperature projections are linear. So here are a couple of climate model experiments from the CMIP2 project at Lawrence Livermore National Laboratory. This one shows 10 climate models projecting what would happen if CO2 increased by 1% a year, every year for 80 years. goes up by a couple of degrees. And this one is from the Special Report on Emissions Scenarios, Scenario A2, which increases carbon dioxide up to about 850 parts per million by the year 2100. And here are some 10 climate models showing what will happen under that scenario. And these black lines in the middle are what's called the ensemble average, which is a fancy way of just saying you take all 10 of them, add them together, and divide by 10. So you get the average projection. That's the black lines. The pink line, straight line, is right in the middle. The only ones that don't have all this noise attached are from this linear model, using the same forcings. And you can see that the pink line goes right through the middle of the climate model lines, also here. And it's very close to the ensemble average. So here are emulations of climate model projections of the Special Report on Emissions Scenarios that appeared in the AR4 2007 IPCC report. In all of them, the points are the projections made by the climate models, and the lines are calculated using our little model of climate models, the linear one. And you can see that generally the lines do a good job of going right through the points. These are a variety of different climate models. I tried to be international. We've got one from Canada. We've got University of Colorado model, the geophysical fluid dynamics model at Princeton. SIL is a French model, and then the GISS model from NASA and UKMO, that's the United Kingdom Meteorological Office, so it's good international flavor. And you can see that this equation pretty much duplicates all of them. So for all their complexity, GCMs just linearly extrapolate greenhouse gas forcing. This is from the RCP scenarios from the fifth assessment report in 2013. Again, we have a variety of different models. The red points are the model projections, and the blue line going through was calculated with our model, our little linear model. And you can see once again that it does a good job of going through the points of all of these projections. For all their complexity, GCMs, these are the current advanced GCMs running on supercomputers. So if you wanted to duplicate the temperature projection of one of these models running on a supercomputer, you could do it with a hand calculator. So for all their complexity, GCMs just linearly extrapolate greenhouse gas forcing. So we now know that GCM air temperature projections are just a linear function of fractional carbon dioxide forcing. The temperature in the year 2100 is just a linear sum of the linear projection of greenhouse gas forcings of the fractional temperature increases year by year by year. So the total error in a temperature for the year 2100 is the sum of the errors in each of the individual projection years. And more typically, you calculate an uncertainty as the square root of the sum of the squares of the errors. That keeps actually positive errors and negative errors from canceling each other out. So error produces uncertainty, and uncertainty gives us a measure of predictive reliability. So air temperature is the thermal content, a measure of the thermal content of the atmosphere. So do climate models actually make a relevant thermal error? And the answer is yes, they do. So from the fifth assessment report, the simulation of clouds and climate models remains challenging, and there's a very high confidence that uncertainties in cloud processes explain much of the spread in model climate sensitivity. And that's true. So this is the results of an experiment taking 25 years of global cloudiness. You can see it represented here. Lots of clouds around the equator. 25 years of global cloudiness observed using satellites. And they reproduced that cloudiness over 25 years using a bunch of climate models. And you can see a black line. This is the cloudiness compressed into a single line, the global cloudiness. So you have the South Pole there, and then you have degrees latitude longitude, here all the way up to the North Pole. So it's compressed, and you can see that they all show that there's a lot of cloudiness around the equator, and then there's kind of a more clear band just north and south of the equator, and then temperate cloudiness. And the black line in the middle is the average observed over 25 years. And these colored lines are the reproductions by various climate models. And you can see that they get the general shape right, but there's a lot of variation of the models around those average cloudiness. So how do you calculate the error? Well, the error is just the satellite minus the model. And that's what this is. So each one of these was subtracted from the observed, and here's the residue. It's quite a bit of it. And you can see that the residue actually has pretty much the same shape as the cloudiness itself. So what impact does global cloud error have on the reliability of projected global average temperatures? So to find out, you integrate the global average cloudiness that was predicted into the past by each of these climate models, you integrate the observed cloudiness, and then you compare and you calculate the root mean square average error. Root mean square is the sum, the square root of the sum of the square of the errors. So you do that, and here's a table of it. So this 66.7% is the global average cloudiness. It says that on average over any given year, 2/3 of the globe is covered with clouds. Here is the average cloudiness from each of these GCMs. And here is their average fractional error. And you can see actually, for example, here's one of the GIST models. It says that there's 65.7% cloudiness, 66.7 is what you observed, but the error is 16%. And the reason it should be, you think it should be small because these numbers are pretty close. But what this is the positive and negative errors are canceling each other out to give you a pretty good average. But if you take the average and square them and add them together, you find out what the true error is. And so these numbers are what's called the lag 1 error autocorrelation, and I'll show you what that is in a minute. But notice that they're all at least 95% or more. So the average error in all of these climate models is 12.1% error in cloudiness. Well, that average cloudiness is worth plus or minus 4 watts per square meter. That comes from a study that was done by Lauer and Hamilton, a couple of climate scientists, a couple of years ago. So that plus or minus 4 watts per square meter is a lower limit of resolution of the simulated atmospheric thermal energy content made by climate models. The total excess greenhouse gas forcing since 1900 is 2.8 watts per square meter, which means that the error in the thermal content of the atmosphere is larger than the total forcing of all of the greenhouse gases since 1900. So the annual average cloud error is plus or minus 140% of all of the greenhouse gas forcing since 1900. So you have to ask yourself, if you have a model, how easy is it to resolve something that's 140% smaller than your lower limit of error? And typically, a scientist would say, you can't know anything about it. We analyzed the error to find out what the error content is. And these are lag 1 error correlations. And what lag 1 is, you take the error from each model and you offset it by 1 point, and then you plot point 1 against point 2, point 2 against point 3, point 3 against point 4, and so on. And if the error is random, you would just get a scatter that looks like this. But you see, you don't get a scatter. You get these nice straight lines, which shows that there's a lot of internal structure to the errors that the climate models are making. So that means that there is systematic data in there that the models are not explaining. And this particular row shows the model error of one model plotted against the model error of another model. And you see you get these pretty good straight correlations, which means that the errors among the models are correlated with each other. So you have an internal correlation showing that there's systematic data left in the error, and the models themselves are making the same kind of error. So what kind of error? So this is a correlation matrix. You take all the models, here's the models over here, here's the models over there, and you plot them against each other and you determine the correlation of one error set with the other error set. There they all are. And here's the error that each model made, right at the end there. And here's the lag 1 correlations again. So you look at these, and there are 66 unique intermodel pairs. 12 of them show correlation of R of 0.9 or better. And 46 of them show correlation R of 0.5 or better. So if those errors were random, there would be approximately 1 chance in 10 to the 17 that any 2 of them had a correlation R of 0.9. And there would be 1 chance in about 100,000 that any 2 of them had a correlation R of 0.5. We have 12 that show 0.9 and 46 that show 0.5. So these errors are not random errors. So the structural coherence of global cloud error made by these models implies that all the GCMs share a common theory error. They're making the same error. So error uncertainty in GCM time steps. So cloud error in GCMs is not random, but it's systematic. And it's inherent in the models and almost certainly reflects an error in the way the theory is deployed inside those models. So how does plus or minus 4 watts per square meter of average theory error propagate in a stepwise projection of future climate? Well, the way models project climate is they start with initial conditions and they calculate the first step in the future climate, and then they take the conditions of that first step, calculate the second step. Take the conditions of the second step, calculate the third step. So this is called the time marching method, and they walk their model through, say, 100 years of climate projection. And typical step sizes are more like 20 minutes, not 1 year at a time. But in any case, they march their way through time using the conditions of the previous step to calculate the subsequent step. So starting with the beginning step right there, so we have the initial conditions of the initial temperature and the initial forcing, and we go forward and we calculate the first temperature. Because of the error that's in the model, say the cloud error, plus or minus 4 watts per square meter, that initial temperature is going to have some uncertainty associated with it, plus or minus a little bit of T up above and below. So you take those conditions and you propagate them forward into the second step, and you calculate a new temperature, and that new temperature also has some error associated with it because of the error that's in the climate model going from step 1 to step 2. But the error that was already in step 1 also propagates forward, so that the total error in step 2 is larger than the error was in step 1. And so that propagates forward. So when you start at 0 and you go out to some 100 years later, the error increases step by step as you go, because uncertainty is propagated because of the error into each subsequent step, and that error builds up across those steps. Theory error does not cancel out. Random error cancels out. Theory error does not. It accumulates. And it produces an increasing uncertainty in predictions of future global average temperature. So uncertainty propagation in a time-wise, we continue with that. Here is figure 5 from the 4th assessment report in 2007. Summary for policymakers showing the special report on emission scenarios, the 4 favorite ones. It's the CCC and the B1 and the A1B and the A2. Showing the model spread, so we have these shadings again, which are plus or minus 90% model spread of the individual models. So how do we make a physically valid reliability estimate of these kinds of temperature projections? Well, enter our model. We know that this equation does a very good job of reproducing the temperature projections of all of these climate models, right up to the most sophisticated versions of them. So what we do is we put the average thermal error made by climate models into the equation. It's the amount of uncertainty there is in the thermal content of the atmosphere for each step because of the cloud forcing error that climate models make. And we use that to propagate the uncertainty through the temperature projection. And here's what happens when we do that. So those, I can tell from the laughter that those, you understand that those are the error bars that you get, and they go right off the page. So that's at the same plot scale. So let's put a plot scale where you get the error bars actually on the page. You can see now that it's plus or minus 16 degrees in order to get these error bars on the page. Those are the identical projections as before. And now you see that they all have uncertainties of about plus or minus 14 degrees after 100 years. So what does it mean to say that something has a plus or minus 14 degree error after 100 years? It does not mean that it's possible that the temperature could be 14 degrees hotter or colder in 100 years. I have yet to find a climate modeler who actually understands that distinction. Excuse me. It means that those plus or minus 14 degrees are well outside of any physical possibility. And what it really means is those are uncertainties, not temperatures. And it means that we just plain do not know where the temperature will be in the year 2100 or any of those previous years. It's complete and utter ignorance about what those temperatures are. That's what that big uncertainty bar means. So you can see I've blown up the A2 up here for the first 20 years, and you can see that here's the A2 projection. That's this one. And you can see that the error bars are larger than the temperature projection immediately, even in the first year. And the reason that they're so large like that is because the annual increase in carbon dioxide is about, the forcing, annual increase in forcing, is about 35 milliwatts per year. But the annual thermal cloud error made by these models is an annual plus or minus 4 watts per square meter. So the difference is that the error is 114 times larger than the variable that they're trying to detect. So that means that the error bars are much larger than the calculated temperature, right from the start. So it's not only that climate models can't predict 100 years out, they can't predict 1 year out. So here is from the fifth assessment report. This is the mean projection of the RCP 8.5 and the mean projection of the RCP 4.5. And when you, again, calculate those using our model and propagate 4 watts per square meter, these are the uncertainty bars you get starting with a projection at the year 2000. So even the most advanced climate models are making errors that are so large that the temperature projections have no meaning. So here's a historical example. This is when James Hansen gave his talk in 1988 before Congress. This is the talk, the testimony that essentially sparked the entire frenzy of global warming into the monster we know it to be today. And here is his scenarios as he originally presented them, scenarios A, B, and C. One of them showed increasing CO2 past what was being produced in 1988. And the blue one is the trend if the 1988 trend continued, and here's what would happen if we sort of cut off emissions. The points are his model calculation, and the kind of more straight lines going through them are calculated using our model, and you can see that it does a pretty good job of reproducing his climate projections. So here's what happens if we propagate 4 watts per square meter of cloud air through them. And you see once again that here are his projections and here are the uncertainty bars. And so his testimony, and you should know that every single time a climate modeler publishes their projections of climate, they look like this and they have the spread, the model spread around it. They never, ever, ever have a physically valid uncertainty bar, ever. So he's actually, he made a double error here of uncertainty, a double misstatement, if you want to call it that, be charitable, is that he not only doesn't have physically valid error bars here, he doesn't even have the spread of his own model projections. So he presented a certainty to Congress that his projections plain did not have. But in any case, here's the true uncertainties of those. So those were completely meaningless projections. So that uncertainty in cloud error makes these projections non-predictive and physically indistinguishable and meaningless. Physically indistinguishable means it doesn't really matter what the air temperature does. You'd never be able to choose which one of these the air temperature is closer to because they're all embedded in each other's uncertainty envelopes. So there's no way to distinguish between them. And finally, from the US National Academy of Sciences, they have a climate change pamphlet, which you can get for free on the web. And they're telling us that the National Academy is where you go when you want objective, dispassionate information about scientific problems worldwide. So here's what they tell us, that the overwhelming majority of climate scientists agree that human activities are responsible for most of the climate change currently being observed, and that model simulations of temperature change during the past century only match the observed temperature increase when the greenhouse gas increases and other human causes are included. So that's the National Academy. So here is a picture from that pamphlet of the projected temperature with natural forcings, and then you put in this carbon dioxide, and those are the ones that more closely match the observed temperature when they're included, when you include both natural and human influences. So I'm sure you know what's going to come next. There's what you get when you propagate through 4 watts per square meter of cloud air. You get huge uncertainty bars, which again makes these two simulations, these projections, indistinguishable from one another in terms of the uncertainties that are around them. You wouldn't be able to tell which one is more correct by comparing it to any observed temperature. So it doesn't make any sense at all to suppose an explanation is possible only when including human influences, when in fact an explanation is impossible, period. So at the end of the journey, projection uncertainty grows much faster than any possible greenhouse gas signal. And large systematic errors make projections of future Earth temperatures entirely unreliable. So what do climate models reveal about future global average temperature? Nothing. And what do climate models reveal about a human greenhouse gas fingerprint on the terrestrial climate? Right? Nothing. Nothing. So at the end of the journey, the current scientific merit of predictions of future warming, there is no scientific merit in those projections. Reliability of the IPCC's warnings of catastrophe, they are not reliable. Evidence of a looming climate disaster from CO2 emissions. You are the doctors for disaster preparedness, presumably being advised to prepare for a climate disaster. People are going to die, and mosquitoes are going to come up, parasites are going to increase. There is no evidence for any of that. So the most rational approach to the problem of CO2 emissions, Christopher Monckton said this, is have the courage to do nothing. Because there is no evidence whatsoever that carbon dioxide is doing anything to the climate. And that doesn't mean that it's not doing anything to the climate. It means that the physics of the climate is insufficient to detect anything at all about carbon dioxide. Because science isn't about what's happening. It's about what we know about what we've observed. In any case, have the courage to do nothing. So that's the end of the story. I'd like to thank critical reviewers of earlier versions of this work. The support, there was no support, no funding agencies, no foundational grants, no business contracts, no under-the-table oil companies, slush funds. It's all my deep pockets. So thank you very much for your attention.
Pat, good presentation. Appreciate it. Could you go back a few slides to one of your error prediction clouds? I had an insight.
Okay.
And a suggestion for how you may want to explain what you have to what we'll call the general public.
Okay?
Well, the thought that occurred to me is if you look at it and you rotate it 90 degrees, it looked like a haystack.
Oh.
And the real global response to temperature
I
over
guess this
time is kind of like a needle. So the models are essentially nothing more than the equivalent of a needle in a haystack in terms of actually being accurate. So
Yeah, you're right. It does look kind of haystack.
it's a haystack,
Yeah.
and what's the real global climate response over time? It's kind of like a needle.
It's about like that, yeah. And they don't know where that needle is or how big it is or what it's made of.
Hi, I'm Scott Replogle. I was with you completely until the very last line of your presentation, and that is the courage to do nothing. You don't need to do nothing. The way humans have survived and prospered on the earth over millennia is not by trying to predict or control how global weather is going to go or growing government to control the climate and depending on that. They've survived by adapting to real climate changes in their local area. So the response is not to try to predict it and control it, it's to adapt to real changes in your climate locally.
No, I agree that the have the courage to do nothing just was with respect to increasing carbon dioxide in the atmosphere. There's no possible way to predict that it's going to do anything. And in fact, if you look at the climate change over the last 100 years, there's no evidence that it's doing anything either. So the idea is to just not worry about CO2 and do exactly what you say.
That does take courage, I agree.
Yeah. Oh, Willie.
Can you tell something about how your attempt has been trying to publish this paper? Please.
That's another story in itself. I've been trying to publish this work for 3 years. And I've gone through review processes now at 6 different climate journals, including some of the major ones, like Journal of Climate. There have been 16 reviews that I've responded to, of which 13 were by climate modelers. The 3 that were not by climate modelers all recommended publication. And the 13 by climate modelers, of course, recommended rejection. I don't know how to say this without sounding self-serving, but every single climate modeler review was incompetent. And by incompetent, I mean they made mistakes that were typical of naive undergraduate freshmen. For example, to a man or to a woman, whoever, they don't neither respect nor understand the distinction between precision and accuracy. They don't understand propagated error, and they think that those error bars that I showed you, these error bars mean that the climate itself, the model, is oscillating rapidly between a hothouse and a greenhouse, a hothouse and an icehouse climate, when in fact they don't mean anything like that. And they don't understand the distinction between an actual energetic perturbation and an error statistic. So they see that plus or minus 4 watts per square meter of error as a perturbation on the model, which it is not. So they make these really, really basic mistakes that if you're a physicist or a chemist, you learn about within the first year of your undergraduate study how to begin to propagate error through your measurements. And none of them seem to know anything about that. So it's been an uphill struggle, and it would be possible to put together a seminar just on that saga alone to show you the kinds of things that they say. It's in 30 years of publishing in chemistry, I have never, ever, ever run into that kind of an experience. It's been really amazing. So, thank you, Willie, for giving me a chance. Oh, yes, yes, sir.
Just kind of scenario, I guess, a little bit to take this one step further. I'm more into the agriculture sector from this area. The global warming, what they're trying to do to us for methane for cattle. You know, they say wetlands puts out more methane than cattle. Just to take it one step further, there's a lot of things in place already working against the agriculture and the public because of the global warming. Is there any other avenues out there? I mean, you guys are doing a fantastic job in what you're doing. Is there any avenues or anybody working on what is projected to happen or will happen, what the government's pushing for? You know, they always talk about Agenda 21, whatnot, whatever. But we can already see things coming in our aspect of agriculture that is created by this that will create huge problems down the road. Does anybody know of anybody working on that scenario, or what's there?
You mean to try and ameliorate that, what's coming for you?
Yeah.
There are probably people who are working on that, but I don't see anybody making much headway against it.
Okay. I'm just kind of curious.
It's one of the most amazing aspects of this whole climate change thing is the way that all of the legislatures and the scientific societies have just rolled right over and haven't done any due diligence at all about it. So I completely don't understand that in any case.
Yeah, and it's, how do we get that word out? What do we do with that? I mean, it is so prevalent out there right now with the NRDs, Natural Resource Districts, USDA,
Yeah.
Your county farm service agency. I mean, it's
pretty
wild.
Everybody should just throw the bums out.
We're trying.
We laugh at them.
Just a quick question. I'm glad Willie asked his question. And I want to tell you, this was really a marvelous presentation. Really, I was going to ask you what the response was. I saw that there were some articles in the Geophysical Research Letters that seemed to form the basis of some of your work, but you're saying that your paper hasn't been accepted. The Annals of Applied Statistics published some work that was sort of contrary, created a controversy. Is that an avenue to look at, and what is the response to, is there an opportunity for?
It's a good suggestion. The paper is under review again at the 6th Climate Journal. It's been rejected one time there. I'm hoping the second time around is better because the editor is a bit sympathetic. I could try applied statistics, but typically what happens is I write to the journal editor and I send them my abstract and I say, is your journal a place that would consider this? And I get no response at all.
Yeah, I mean, the journal editor, they did quite a job. McShane and Weiner, was that who it was? And devoted a whole edition to that. So, and it looks like you have profound autoregressive disorders that they would be quite interested in. So you just wonder if you sidetracked some of the mainstream climate stuff. But anyway, it was really a wonderful presentation.
Thank you.
Very good.
But it's a standard analysis, and this could have been done and should have been done 25 years ago. It could have been done 25 years ago, and if it had been by somebody in the American Physical Society, very straightforward analysis of propagating error, this whole thing would never have happened. So thank you.